Hello everyone, myself Yadagiri, Assistant Professor, Department of Electrical and Electronics Engineering, MLR Institute of Technology, Hyderabad. The last session we have discussed about the module number 1, that is the DC circuits, that are we can say the unit number 1, that is the DC circuits. In this module, we need to discuss about the AC circuit. That is the second module of the subject, that is a BEE. So that is AC circuits, or we can also say the unit number 2 in the BEE, that is the AC circuits. So before going to involving into the whole AC circuits, first we would like to discuss about the fundamentals in different fundamentals or different concepts in AC circuit. So next we need to go with the first concept of the second module, that is the introduction to sinusoidal waveform. So here sinusoidal sinusoidal waveform is nothing but it is a AC. The AC supply or AC signal is nothing but sinusoidal waveform only. So why does it say like that? Means if we have the other alternate signals like triangle, then also a sawtooth, like so this is the sawtooth, this is the sawtooth waveform. Also we can consider, and also the stepped waveform, and also this one. So it is also kind of alternate quantity. So these are stepped stepped alternate quantities, and also other signals are there, that is rectangular signals. It's also alternate quantity. So this one. So that is the square wave, also an alternating quantity. So these many things, but we should say AC signal means we are always concerning about the sinusoidal only. So reason behind that is, if you are able to multiply the two different sinusoids, you will get again, or we will get the sinusoidal wave as a resultant. If you are able to add the two different sine waves or different sine signals, again we will get the resultant as sine only. So if you are able to add the different triangular signals, we will get the stepped waveform. If you are able to integrate the different kinds of the rectangular waveform, then we will get the square waveform, like that. So based on that analysis, so AC means AC signal means always we should consider about the sinusoidal only. Reason, if you are able to add, or if you are able to addition, or if you are able to differentiate, or if you are able to multiply the two different sine signals, we will get again sinusoidal signal only resultant. Resultant as sinusoidal signal only. So for that reason, AC signal means sinusoidal signal only. So for that, sinusoidal signal means AC signal. So here sinusoidal waveform means it doesn't mean that only sine wave. It's also considered as a shifted sine wave. It's a pure sine wave. It's a shifted sine wave. Sinusoidal waveform doesn't mean that only sine wave. It's also considered as shifted sine wave or cosine waveform. So that's why sine means, so it's only the pure sinusoidal, either the shifted or the cosine waveform. That's also considered as a sinusoidal waveform only. So here we need to discuss the standard waveform. The standard form of, or general. Every standard textbook followed the standard notation. Standard form of the sinusoidal waveform. Sinusoidal waveform. So that is, let us say it's an x, this one as an x, this one. So the time we need to consider in terms of the either omega t, that is omega t, this one. So we need to represent this the sinusoidal signal in terms of notations, or in terms of mathematical notation. So that is a x of omega t equal to, so here we have taken as a omega t, that's why it's a x of omega t. If it is considered as a t, then we can take it as a x of t, either the x of t. So that equal to, so this is peak value or the amplitude value. So that x max, x of omega t equal to x max cos of omega t plus or minus alpha. So also some people are following the notations like that is a x of again omega t equal to, so xm then sine omega t plus or minus alpha. So this is the standard or generalized notation of the sinusoidal signal. So every standard textbook followed the same notation. So this is the representation of the sinusoidal waveform, that is x of t equal to xm sine theta or sine t simply, or x of omega t equal to xm cos omega t plus or minus alpha. Here alpha always indicating as the shifting angle of the signal. So this is alpha. If you are able to move the signal like towards left side, let us say. So let us say the signal considered from the So starts from here, from this point. So this we are going to get like this. I mean the corresponding angle and the corresponding angle of the signal should be, I mean the corresponding shifting angle of the signal should be like this. I'll take it as this one. So this is the signal starting point. So this angle is a something negative angle. So if you are able to shift the sine wave towards the right side, then the alpha value should become negative. Then if you are able to the shift the signal like, if you are able to shift the signal like, so towards the left side, I mean to say you need to start from here like this. So this is with respect to t, and the corresponding signal like I or v, so it's also v or I. Then this corresponding signal value, I mean the shifting angle of this corresponding signal should be so something value, that is alpha. So that is in terms of plus. So if you are able to shift the signal towards the left side, then the shifting angle should be considered as a positive. So based on this one, we can represent the alpha value. So this is the standard and generalized form of the sinusoidal signal, that is x of omega t equal to x max into cos omega t plus or minus alpha, either this or this one. So we can consider either this or this one. So this is about the, I mean introduction about the sinusoidal waveform. So sinusoidal doesn't mean that only sine wave, it's also a shifted or cosine wave also we can treat it as a sinusoidal waveform. So this is the introduction to sinusoidal waveform. So next we need to find out the effective values of the different signal. Let us take this one. So I'm going to find the effective value of the different signals. Like so I'm going to take this signal is called fixed DC signal. It is a fixed DC, and this one the pulsating DC we can consider pulsating DC. This one is a pure AC signal or pure sinusoidal signal. So let us take suppose this value should be as 20. Let us take either 20 volts. Here we have considered as a voltage, means it's a 20 volts. So for suppose this one the starting instant is here, this one, yeah, this one we can take this one 0, let us assume. So this value should be as 10, let us say. So then for suppose this one 0, here this is I mean plus 5 volts. So this is, for suppose it is a minus 5 volts. So based on these values, we would like to find out the effective values of the different signals. For fixed DC signal, the effective value should be the effective value of so the above signal is, so how much it is fixed to 20 only, I mean, so 20 volts, and the effective value of this signal we want to say that is 20 only based on this one. So here also 20, here also 20, here also 20. That's why the effective value of this corresponding signal should be 20 only. So for suppose coming to this one, here 20, I mean sorry, either 0 and this one 10 and this one for suppose again 0, and for suppose here 10. So are we able to, I mean find the effective value of this one? Either we need to say either 0 or 10. No, we can't say like that. So we neither confirm as a 0 and also not should say like 10. So then how can you get the effective value of this one? Means, so the effective value of this signal, should be how much? It's an average of these two values. If we are going to consider the average of these two spans, then we will get the exactly effective value of this one. Means what I want to say means, it is a time invariant signal. The time, I mean the signal magnitude will not vary with respect to time, so that the effective value of the time invariant signal should be fixed only. That is whatever the magnitude maintained by that signal, that is the effective value of the signal we can say. So for this one, it is a time invariant signal. So it I mean it's a time invariant signal. This one time varying signal. So we will get the changes, the magnitude of the signal with respect to time. That's why it's called time varying signal. So if you are able to get the effective value of these corresponding time varying signal, so the effective value will be average value of that. I mean to say, we would like to consider we would like to calculate the average value of this signal. So that is called as simply effective value. So that the effective value of this corresponding signal should be average value we can consider. That means, so it's a 0 plus 10 by 2 we can say, we will get 5. That is, so I mean the 5 volts or 5 ampere or something 5x as the effective value of the signal. So if you are able to get the effective value of time varying signal, we would like to consider the average value. So same method we need to, or same strategy we need to apply to this one. Then what we will get? So it's also a time invariant, sorry, time varying signal. So if you are able to get the effective value of this one, the effective value of the above signal, effective value of the above signal is how much it is. So we have considered here the average. Here also we can consider the average value. So the average value of this one, that is a plus 5, then minus 5, will get 0 only. So then we can't, we can't get the exact effective value based on average value. So for this reason, we need to do the squaring of the signal, means we need to consider the square root of the signal. So then after that, we need to find out the average after that. That means, so other name of the average means mean value. So mean value, then we need to do first the squaring of the signal. Then after that squared signal, we need to find out the average value. That means mean value. Then after that, we need to find out the roots of the signals. So then we will get so these roots of the signal will giving us the effective value. So this root means, if you need to indicate this one in terms of shortcut, that is a root mean square. So that simply, so we can confirm the word is, that is, if you are able to get the effective value of this kind of time varying signal, you would like to find out the RMS value. This is RMS value. The effective value of this one, if you are considered as based on the average, then that will get 0. So that we need to do the squaring of the signal. We need to do the squaring of the signal. After that, we need to find out the mean value or average value. So it is the square of mean of the mean of the above signal. Then based on that, we will like to find the roots. So that corresponding thing we can consider as a RMS value. So means the effective value of this time varying signal, we would like to find the RMS value. So this is the effective value of the signal. This is the effective value of the signal. So the effective value of so this kind of time varying signal is the average value, and the effective value of this corresponding signal is that is RMS value. So for any kind of alternating signals or alternating quantities or sinusoidal signal, so we would like to find out the effective values based on the average and RMS values. So this is the first thing we need to discuss about the average value of the sinusoidal waveform. So here let us consider a sinusoidal waveform. So we would like to find the average value of the sinusoidal waveform. It is a sinusoidal waveform. So for suppose we need to take the current of this one. So the current is, so that is so the current in terms of I equal to Im sin theta. So it is the instantaneous value, so that we can mention it as in terms of the small letters. So we have already discussed about that is in the beginning session. So that is I equal to Im sin theta. So need to find the so the average of this one, that is I average equal to the, what we want to find here. So we need to find the effective value of the sinusoidal waveform, this kind of thing. That means average value we need to find. So that we need to find the average value of sinusoidal waveform. So if you are able to get the average value of this waveform, we need to consider the area of one alternation. So area of one alternation to the total base length. Area of the one alternation to the total base length. So that will give the average value of the any signal, either the voltage or current, both. So here only we can consider the one alternation because it's a symmetrical wave. For unsymmetrical wave, we would like to consider the complete cycle to get the average, the area of that corresponding signal. If you are able to get the complete area of the symmetrical signal, we will like to consider the full cycle or complete cycle. So for symmetrical signal, if you are able to get the area, or we can say average value, we only consider the half cycle. So based on that one, area of the one alternation to the total base length of that alternation. So here area means integration 0 to pi. So it's 0 to pi, that is one alternation or one alternation. So the area should be, this is the current, so that I into d theta. So divide by pi minus 0. I into d theta pi minus 0. Then I average equal to, so this is the expression number 1 we can consider. Then substitute the I value here. So that is integral 0 to pi. Then I value is the Im sin theta, then d theta. So this one either omega t or theta we can consider, because just now we have discussed about the angular velocity or simply angle, that is in terms of radians only always. So Im sin omega t divided by pi we got. So after simplification we got it as Im by pi integral 0 to pi sin theta into d theta. Then after the integration we will get I average equal to the that is Im by pi minus cos theta. After applying the limits, then the complete average value of the above signal is, I mean sinusoidal waveform is, it's a 2 times of Im upon pi. So this is the average value of the sinusoidal waveform. So this is the average value of the sinusoidal waveform is this one, that is a 2 times of Im upon pi. So it's also same for pulsating DC. So because it's also symmetrical waveform, if you are going to get the average value of the pulsating DC, that is a rectified DC, so we'll also we'll also do the same analysis. For that also we will get the same kind of average value, that is 2 times of Im upon pi. So this is the average value of the sinusoidal waveform. Then the root mean square value of the what that is again sinusoidal waveform. So the root mean square of the sinusoidal waveform, here we have considered as a V. So here V instantaneous value V equal to then V max sin theta. So this is equation number 1. If you are considered as a current, that is I equal to Im sin theta. Then we need to find the VRMS, root mean square value. So that is square root of that is the area of squared waveform. Area of the squared waveform of wave of one alternation, that is one half cycle, half cycle, simply one alternation upon the total base length. Area of, that is the area of the square of the one alternation to the total base length. So that equal to the square root of integral 0 to pi, that means Vm sin theta square, means that the Vm sin square theta into d theta divided by pi minus 0, and we will get square root of Vm upon pi, then in bracket we will get that is a sin square theta d theta, then sin square theta d theta, then here Vm square, we got the Vm square here, I think Vm square, then we will write outside this one as in terms of Vm by root pi, then square root of, so if you are replaced this whole term with the 1 minus cos 2 theta by 2, that is integration as it is, here also integration as it is 0 to pi it is, here also integration as it is 0 to pi, then so Vm by root pi, then square root of integral 0 to pi 1 into d theta minus integral 0 to pi, then integral 0 to pi, it is a cos 2 theta by 2. The cos 2 theta by 2, after simplification we will get the VRMS of the sinusoidal waveform should be Vmax, Vm by root 2 we got. After simplification we will get the VRMS value is in terms of the Vmax upon root 2. If it is considered as a IRMS, the sinusoidal waveform as a current, then we will get that is a Im upon root 2. So this is the RMS value of the sinusoidal waveform. So this is the RMS value of the sinusoidal waveform, and the previous one is the average value of the sinusoidal waveform. So if it is a voltage value, so that the V average equal to the, that is a 2 times of Vm upon pi. So this is the average value of the sinusoidal waveform for voltage. So next based on that one, now we need to discuss about the form and peak factors. So the form factor is a ratio of the RMS value of the any alternating quantity to the average value. If it is a sinusoidal waveform, we would like to consider the RMS value. It's a ratio of the RMS value to average value. So the form factor of the sinusoidal waveform, it is the ratio of the RMS value to the average value. The RMS value of this one is, so just now we have derived, that is IRMS by root 2. Then it is a 2 times of Im by pi if it is a current. Then here we will get, that is a 1.11 after simplification. Im gets cancelled here in the simplification. Then we will get the 1.11. This is the form factor of the this one. That is the form factor of the sinusoidal waveform should be 1.11. So it's always denoted by the kf, that is a form factor kf. So kf equal to, we can write the sinusoidal waveform 1.11. So it is a different value for the square waveform and also the other alternating quantities. So this value 1.11 is the form factor value of only sinusoidal waveform. So coming to this one, we will get the peak factor. So it's a ratio of the peak value to the name itself will get the information, that's a peak value. So it's the ratio of the peak value to the RMS value, that's simply called peak factor. So based on the simplification, we will get the sinusoidal waveform peak factor value, that is the peak and form factor. So this is the fun introduction about the different kinds of the signals and also the sinusoidal waveform. So in this session we have till now discussed about the, so what does it mean by alternating quantity? So alternating quantity, nothing but it is a voltage or current, so we change its polarity and magnitude at a regular interval of time. It's simply called alternating quantity. And also we can say alternating current. Then after that we have discussed about the instantaneous values and the magnitude of the signal, and also the amplitude value of the signal, and also what does it mean by time period, and also what do you mean by frequency. So these many things we have discussed. So here the time period means instantaneous value means it is a different instant with the corresponding values, simply called instantaneous values. So we need to consider any instant of the signal, then the corresponding value, we can say it's a magnitude. So it is a peak, it's a high value or the maximum value. So it is a maximum magnitude of the any quantity, it's called simply amplitude. Then after that we have discussed about the time period. Time period means it's a minimum time, it's a minimum span of the signal or minimum time or value of this time, so which separate the repeated waveform, that's simply called time period. So if you are able to do the reciprocal, to say the 1 by t, we can say time period, we have to represent the time period with the capital T. If you are able to do the reciprocal of time period, so that will give the information about the frequency. Frequency means how many cycles are coming in the particular second, that's called frequency. Simply say cycles per second. So cycles per second is a frequency. Then after that we have discussed about the cycle and also the after cycle and also the angular velocity. Angular velocity, the omega, so that is equals to the theta upon t, which means theta equal to omega t. Either instead of time, either we can consider either theta or omega t, both are in terms of radians only. So then after that we have discussed about the introduction to sinusoidal waveform. So the sinusoidal doesn't mean that only sine wave, it's also a shifted sine. So shifted sine also we can consider as a sinusoidal waveform only. So from this one we need to take the standard notation of sinusoidal waveform, it is a xm sine omega t, so plus or minus alpha. So this is the generalized or standard form of the way of representation of the sinusoidal waveform. So then after this we have discussed about the effective values of the different signals, like fixed D signal and also the pulsating D signal and also the sinusoidal waveform. So this is many things we have discussed. So if it is a fixed signal, the effective value should be fixed only. If it is a pulsating DC, the effective value should be considered as an average value. So if it is a the alternating signal, then the effective value should be RMS value. So then after that we have done about the average value of sinusoidal waveform, that is, so we got as 2 times of Vm upon pi we got. Then also we have calculated the RMS value of the again sinusoidal quantity, that is RMS value equal to, that is a Vm upon root 2. Then after that the Kf, to say the peak factor and form factor. So peak factor nothing but it is a peak value to the RMS value, that's simply called peak factor. So and also we have done about the RMS value of the sinusoidal waveform, that is RMS value. Then after that we have also discussed about the form factor of the sinusoidal waveform, that is the ratio of the RMS value to the average value. So based on that, So we will get the RMS value and the average value and also the peak factor and as well as form factor. So this is the introduction to the whole AC circuits and as well as the only the sinusoidal waveform. So this is introduction to sinusoidal waveform. This is the fundamentals in AC circuits. So in this session we have completely discussed about the fundamentals in AC circuits, and after that introduction to sinusoidal waveform. The next session we need to discuss about the phasor representation of the sinusoidal waveform. Then after that we need to go with the different kinds of analysis about the resistor, inductor and capacitor. So this is the end of the session. Thank you and all. Thanks for watching.